Next up, I welcome Melinda Xiao-Devins, Senior AI and Machine Learning Manager at Zoom Communications. Today, she's here to present her talk, From Big Data to No Data and 2 Use Cases in Machine Learning. Checking in also, how is everybody doing? Are you guys enjoying the event? I hope you are. Drop us a note in the discussion area and please let us know what you think. We want this to be the best experience for you. And don't forget, all of this content is going to be available on demand for 2 weeks after we go live today.
Oh, hi, everyone. Thank you for attending this data science salon. I'm going to talk about 2 use cases, very typical use cases from big data and to no data. First of all, let me introduce myself. I'm the senior manager for AI and machine learning at Zoom Video Communications, and I'm leading a large team here to build machine learning solutions for Zoom. But the use cases I share here are very typical to a lot of companies. And the first use case is the case that you have infinite data. For example, take a recommendation system as an example. It's essentially a problem of information filtering. And you filter out a massive number of items and recommend small sets of items to the user based on user's interest. And it's a personalization problem here. And industry has decades of practice in here. A lot of companies such as Netflix, Amazon, YouTube, Facebook, and the game companies Steam or some lately very popular TikTok, they all have their own recommendation engine built. So it's a very mature machine learning problem. And from the data side, you are collecting the data from user clicks, browsing history, search history, purchase history. And assuming you build a feedback loop into the application support event tracking, so you have a feedback loop. And that data is essentially labeled by the user's activity or the purchase history. The problem to solve here is dealing with a large volume, high speed of the data. And technology involved here, first of all, is choose the platform. And Apache Spark is a very popular platform in building the recommender system. It supports the batch processing as well as the streaming data processing. And lately, the Apache Flink is support the native streaming and provide near real-time performance. From machine learning algorithm point of view, it's also very mature practice here. You've got content filtering, and you got a collaborative filtering, and you also have the deep learning algorithm to choose from. The main focus is select candidates of the items and rank those items. And it's very important to build a feature store here. And from the different components of the project, there are involvement in cloud infrastructure. And in some cases, if you want to build a Spark platform for the ETL, the data extract, transformation, and load, and you also need to execute machine learning jobs on the Spark platform. If your choice is AWS Cloud, then AWS Cloud EMR, AWS EMR offers that solution, and that you can have a managed cluster and to do the job. So you don't have to deal with bare bone hardware or very low level infrastructure, and you can focus on building your application software on top of the cluster that's being managed by AWS. Other public clouds also have a Spark solution, which I may not be familiar with. I'm more familiar with the AWS solution. And then another thing to consider is the Spark job orchestration. Airflow is a very good to use, and there are other orchestration software as well. And building the feature store, what you want to consider is a feature being mutable. If it's immutable, of course, you can put your Hive table. But if it's mutable, the latest technology pointing to Apache Hudi on the S3 in case of the AWS cloud. And for the, of course, you need to think about model serving, how you serve that model. If you want to build your own Kubernetes cluster in AWS cloud, you can use EKS, or you can have a Kubernetes cluster in other clouds as well. And all that is being supported by most public cloud platforms. And another aspect is the big data engineering. And you need to have big data engineers to deal with the data injection, Spark streaming, or data ETL. And of course, machine learning engineers. And in this space, because of the infinite data set, and you want to stay with the Spark ML. And Spark ML lately has supported a lot of NLP libraries, and computer vision is another one. But when they come to the deep learning NLP or computer vision, you may build a separate model serving pipeline to serve those deep learning models. So that's a technology stack. Now, the second case is when we're dealing with too little data or no data. This is because as a platform, the content of the data content, it belongs to the user. The user owns the content of a communication, such as images and video, audio, or transcript. And the platform do not have the ownership for that user content. And user may not give the platform the permission to utilize that content for machine learning purpose. On the other hand, it's also very difficult or almost impossible to anonymize the content, such as however you try to anonymize the image, video, or audio, it will still, the personal information can still identifiable. You can still tie that content with the user. So there's no way you can completely remove the PII from the video, image, or audio, or transcript text. So how to solve the problem when there's no data or little data? This is quite different with a big data problem when you have a large amount of data. Here, you literally have no data or very little data. So you can try to solve the problem from a data point of view, like utilizing the open source data set, or buy the data set that's similar with your production data, or synthesize the data, try to simulate the data. That's how to solve the problem with the data. From the data side, you try to enhance your data set. Now, there are other solutions. And supposedly you have a pre-trained model trained on the open source data set, and that's good enough to do the job. And you can try that open source pre-trained model as well. Hugging Face offer a lot of pre-trained models. Or you can rephrase the problem to be a cluster problem, unsupervised learning problem, plus some rule-based software. If that can do the job, and congratulations to you. However, there are also other aspects in the industry's latest practice. Meta-learning opened the door for us to explore the lack of data problem from the deep learning modeling aspect. So like a few-shot learning, and rephrase the problem and make it as a task to learn the similarity and differences of the items. We get around the problem of a classification, which needs a lot of data to train the classifier. So I'm going to talk on the top level how the meta learning works, how the few-shot learning works. And you have two tasks. And the real task is a task you want. You want to build a classifier or some kind of model that can classify 3 different breeds of the dogs. For example, here, Labrador, Saint Bernard and Pug. However, supposedly you don't have label data for that 3 grade to build a classifier, or you don't have enough data. You only have a few examples. In this case, you have 3 classes. You have 2 examples for each class. So we call that a 3-way 2-shot learning. And way is n-way k-shots is typically n-way represent the n classes. K-shots means on each class how many samples you have. In this case, it's a 3-way 2-shot learning. And classifier just doesn't work because classifier will require a lot of data. But what you have is a large corpus of the different other breeds of the dogs, for example. And you have a base data set. It's a large data set. You just don't have the specific label for the problem you are solving. So you need to construct a neural network to do another task. And this task will train on a large labeled data set and will learn, this task is target to learn the feature embedding and the similarity. And when you do the prediction, which is the meta testing phase, on the meta testing phase, you can use your few examples, the 2 examples for 3 classes, that's your support set, and then compare the data of the query set, which is the images you want to predict, with the support set image. Find the similarity, and you will know which the dog breed is from the support set image. So that's on the top level. It's a very brief introduction about the few-shot learning. And few-shot learning is an area in the meta-learning. So we're going to look at some of the more detail. And so for the metric learning, there's one aspect of the meta-learning is called metric learning. Metric learning is targeting to learn a distance function between the images. And we will extract, during the meta training phase, we will extract image embedding. You can use a CNN network to extract embedding. Or you can also do some other embedding as well. And each query is classified by the distance to the support set. And you can use a Euclidean distance and classifier. You can use a k-nearest neighbor as your classifier. So during the meta training episode, and the key is to construct the loss function. The loss function, the loss will back propagate it to update the CNN parameters. So after the training, your CNN parameter, which is your embedding, and your distance function is trained to tell the similarity and the dissimilarity images. And there are many ways how to extract feature and how to compare the feature. So there's a lot of room for creativity here. And there are other networks can do like a matching network for one-shot learning. The first paper was published by Google DeepMind. And this is in the area of metric learning. And it's pretty much the first example in the metric learning. So it can extract a feature for both support and query set and refine those features using LSTM and compute the query label using cosine similarity with the support set. And the other network, and there are a relation network published by the universities, several universities, Britain. And the relation network works as extracting feature maps for the support and query set, and compute the they compute the prototype. The prototype is a mean of each class support features. And then the prediction is to concatenate the query feature map with each class prototype feature map and feed into a relational model. And the relation model can output a relational score. And that's a relation network. And the state-of-the-art model right now is a prototypical networks. PhotoNet is published by University of Toronto with several researchers in the University of Toronto published the first paper. And PhotoNet works in extract the feature vector for the support set and query set and compute the prototypes. Prototypes is the name of the support features for each class. And it will predict the query set using Euclidean distance to the prototype. And there are also other networks, many papers being published in the contrasted learning field. Constructed learning, again, is also a neural network tool targeting to find the similarity and the dissimilarity items. And it used another aspect using the self-supervised learning means they construct positive and negative pairs. Of course, you can your positive and negative pairs you can annotate it, or you can use a self-supervised way, like you can mask certain area of the token, then you have a positive sentences in area of the NLP, or you do some tricks and you have a positive similar images or dissimilar images. And then you use a encode that you build encoding architecture. And the key here is to build a loss function so that in the feature space, the similar items stay close and the dissimilar items stay far apart. And then the many ways you can try in a similarity measure. One is a cosine similarity, mean square error similarity. So again, contrastive learning involved the construction of the positive and negative sample. And there are many experiments can be done here. And many creativity can be utilized here. And also the embedding loss function. So that's a way, those are the several main developments in the deep learning space. So here we talked about very briefly about two extreme use cases. One is a big data use case where you have an infinite data set, and technology focus is to dealing with the data speed, the high volume and high speed of the data. Another use case is machine learning, especially in the area of computer vision or NLP. Due to the data privacy, you literally don't have any label data, or only have a small sample, less than 10 samples, for example, for each class. And then the latest development in the meta learning and in the computer vision or NLP can help us solve the small data sample problem.